Okay, so welcome back to another video, and in this video I will be explaining how to perform molecular simulation dynamics with the docking that I had performed earlier in my episode number 1. So I will be using the pose that I had created in this episode number 1, which is right now shown in front of you. So this is the playlist which I started with, and I did the molecular docking in the first episode by making use of UCSF CHIMERA and Autodoc VINA, and the output file of this docking that I had performed, I will be using that output file for performing molecular simulation dynamics using Gromacs. Okay, so briefly talking about the docking that I had done in that previous video, I took D2 dopamine receptor and then I performed the docking with the drug, which is the risperidone drug. Okay, so I took the receptor and the ligand, that is a risperidone, which is represented in this paper. I performed the molecular docking, and the docking that I had performed, the entire folder, if you just go through the episode number 1 video, that entire folder is there on my screen right now. And for that, what I will do is that I will open the folder. If you don't know what I have done and how I have created all these folders, you just go to that episode and just have a look at it. So in that video, you will come to know that I have created a folder which is a risperidone, and over here the PDB file, which is the pose1 file, I will just copy this file, and for now I will just paste it onto my desktop. Okay, so this is the file which has the protein as well as the receptor. The receptor which is there inside this this protein is the docked ligand of risperidone. So just let me just open it once so that you can get the clear idea. So I have opened UCSF CHIMERA and I will just open the file that I have kept on my desktop. So pose1 is the file. So as you can see over here carefully, this is basically the protein ligand complex. So as you can see over here, so the ligand is represented over here with the green boundary. So just let me change its color just for your visual. Okay, so we will take this complex and then we will do the molecular simulation dynamics. One more thing that I want to tell you over here is that whatever codes and the commands that I'm going to share with you, those will be the universal codes. You can use your protein, your ligand, your complex. You can run the exact same codes with no changes to get the identical results. Okay, so for that, what we will do is that I have compiled the codes, and the codes are available on my Github repository. So this is basically the place where I have kept all the files and the codes. I will leave the link of the in the description of this repository in this video. So for now, let us just begin with this tutorial. So what we will do is that we want to download all these files. So I will just go to this green button over here. I will press on the code and I will then go to this download zip. And now I will download this entire compressed folder and save it onto my desktop. So over here, what you can see is the compressed folder that I have just downloaded from my GitHub. I will simply extract it onto my desktop again. Okay, so this is the downloaded zip file that I will not be using for now, but I will be using this folder, which is the extracted folder, and I'm just keeping it on the right hand side of my window so that you can see it properly. So now if I just open this folder, there are 1, 2, 3, 4, 5, 6, 7 and 8 files over here. And if I just open my repository, if you just count 1, 2, 3, 4, 5, 6, 7 and 8. So all the 8 items I have downloaded and I have just opened it and kept it into a single folder. Okay, so the first thing that we will do is that we will open the codes that are required for performing molecular simulation dynamics with the help of Gromacs. Now, if you are coming here for the first time, I have created a video onto my channel, and if you just go through this video, which is episode 8 and episode 9, this is where I have explained how you can set up your system by installing the tools and the softwares that are required to perform molecular simulation dynamics. So once you have gone through these 2 videos and once you have downloaded and installed all the softwares, necessary softwares, you are good to go. Okay, so without wasting any time, let us begin. So what we will do is that I will open the folder which I have simply downloaded from my Github. And into this folder, there is this important file which says Gromacs code. So I will double click over it. And as you can see, we will start performing the Gromacs, and the steps for performing the molecular simulation dynamics with the help of Gromacs are mentioned over here. Okay. So I will just go through it one by one. Okay. So for now, I'm simply minimizing it. Whatever I'm doing right now is there inside this tutorial. Okay. So, okay, fine. Let us begin. So I have the pose one, which is over here. So simply you first copy this file and paste it inside the folder where we are working. Okay. So we have pasted the protein file inside this folder where there are multiple files. Okay. Now, what we need to do is that in molecular simulation dynamics, we first need to create topology, and the topology of protein, which is the receptor in this case, and the ligand is to be done separately. So we need to split the file of complex into receptor file and the ligand file. So I will just show you how it is done. So this is the first part of the tutorial where we are trying to create the topologies of the protein as well as the ligand. So for that, we will simply go to this CHIMERA. I will open this CHIMERA. I'll just full screen it. I will just go to the I will go to this option which says file and open. Then onto my desktop, if you just see, there is this folder which says Gromacs Protein-Ligand main. So I have this folder where I will be working. So this folder is basically will be considered as the working directory for now. Okay. So I will open this pose one and I will simply open it up like this. Okay. So I have my protein as well as the receptor inside this complex. So I will first split this file into 2 sections. So for that, I will first select the chains. Okay, so I have selected the protein chain, whereas the ligand is not selected. So first of all, you select the chain of the protein, go to this option which says actions, atoms and bonds, and you delete it. So here what is left with us is only the ligand. Okay, so to save this file, what you need to do is that first you need to add hydrogens to it. Okay, so you just go to tools, go to structure editing. Okay, and there is this option which says add hydrogen. So you simply click over it, add hydrogens, you press OK, keep everything as defaults, and the hydrogen has been added. Okay, so this is the ligand. We have removed the protein chain, so the ligand is there with us. We have added the hydrogens, and now we are going to save this ligand into the mol2 file. So for that, we will go to file and we will go to this option which says save mol2. I will press over it, and into the same working directory, which is the Gromacs Protein Ligand main folder, I will just save it as LIG in capitals. Okay, so you have to do the same thing. You also have to save the ligand file in capitals and just give it the name LIG in capitals. That's it. Okay, do not give any other name, just give the name like lig. Okay, and simply save it. And when you save it, make sure that you are saving it into the mol2 file. So you have to keep the small box ticked, and you just press on the save, and I will close the CHIMERA for now. Okay, so this is the folder where we are working, so which is called as Gromacs Protein-Ligand main. So I will just open it once, and as you can see, I have created this file which is the lig.mol2 file. Okay, so this is lig.mol2 file. So the first step is done. We have deleted the protein chain and have kept the ligand and have saved it into the mol2 file. Okay, now the same thing we have to do for the protein chain. So we have to separately save the protein chain which does not have the ligand. Okay, so again we will open CHIMERA. Okay, and we will go to this option which says file. So we just go to file, we'll go to open. We will go to this folder onto the desktop, which is this Gromacs Protein-Ligand main. So we'll go to this folder which says Gromacs Protein-Ligand main. You just open it. Again, open the pose one. Okay, so this is the complex that we have. We'll just zoom it a little. And at the same time, what I will do is I will keep this folder over here so that you can get the idea what I'm doing. Okay, so over here, I will now, in this case, I will delete the ligand but keep the protein. Okay, so for that you have to go to select, go to the chain. We have selected the chain, but in this case we have to delete the ligand. So I will again go to chain. I will choose the second option. So second option, as you can see, it is the ligand. So ligand is selected, and then I will go to this option onto the menu bar, that is actions. Hover my cursor over atoms and bonds, scroll it down and press on delete. So I have deleted the ligand file or the ligand from the protein molecule. Now, before saving this file, what I want to do is that we have to go to this tools. Then we have to go to this option which says surface/binding analysis. Hover it down, hover your cursor down and go to this option which says doc prep. Okay, so you just press on the doc prep. Another window will open like this. Now over here there is this small tick box which says incomplete side chains and replace using Denmark rotamer library. So you uncheck this. So you have to uncheck this option, and secondly you also have to uncheck this write mol2 file. So these two options you have to uncheck. Keep the other options as it is, don't do any changes, and press on OK. Now there is this option that is coming. It says add hydrogens to doc prep. So we will do OK. Then assign charges, select guest tiger and press OK. And it says specify net charges, let it be 0. Select guest tiger, which is the default option, press OK. Press close. So here, as you can see at the bottom, it says doc prepped finish. Okay, so there are few remarks that came, but you don't need to worry about it. The doc prepped is finished, so let it be. Don't need to worry, there is no need to worry. Now what you do is you go to this files option and then you save it as save pdb. So you just simply save it as save pdb. Now when you're saving this file, make sure that you are saving the file in this working folder which is there on the left hand side. The name is Gromacs Protein-Ligand main. So you select the same name over here on this small window, and here you have to give the name REC for receptor. Exactly this name you have to give for your file, and then you have to simply press on save button. Okay, so as soon as I saved it, as you can see, just close this. I have what I have done is that I have made the splits of the complex. So this is the complex which contains both ligand and as well as the protein. I have splitted it into two sections, ligand and the receptor. The ligand has to be in the mol2 file, whereas the receptor has to be in the pdb file. So these two files are mandatory. Okay, so now let me just open the tutorial which is there, and as you can see, I have prepared the ligand and the receptor in CHIMERA. So this part has been done. Okay, now what we need to do is, we have to, first of all, it says open the lick.mol2 file, and in the second line there has to be a correction that has to be made. Okay, so I will just show you what they are trying to explain. So right now what you do is, to open the mol2 file, what you do is, inside this folder, simply right click in the empty space, select this option which says open in terminal. Now the terminal has to open inside this folder, and if you can see the name of the folder where we are working, which is the working directory, it is mentioned over here. Let me just zoom it a little. Okay, now to open the lick.mol2 file, we will give the command which says gedit lig, and press tab button and hit enter. So your lick.mol2 file has opened over here. Okay, onto this folder. Okay, so now you just see what changes you need to make over here, right? So let us just see the changes that we need to make onto this file. So you just go to this Gromacs codes, and now it says that there has to be something which is says tripos molecule. So it is there over here, tripos molecule. So this has to be the first line. If there is something above this, okay, if there are some other things on the top of this line, then you have to delete those things. Okay, but here in this case there is nothing. Okay, so this has to be the first line. As you can see on the left hand side, the number 1, it means this is the first line, and the first line of the mol2 file has to start with this @tripos molecule. Okay, so that is done. Now you just go to this command, this tutorial, and then it says there will be the name after these lines, maybe like some pdb or something like star 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 or anything. Just change it to lig. Okay, so I will just show you what we need to do over here. So below this line in the mol2 file, there is this name written which is saying pose1.pdb. You just delete this and you have to write lig. That's it. And you press on the save button and you close it. Okay, so this is done. Now as you can see, we are working, the terminal is still open in this working directory, and we have to run a small script which says perl script mol2.pl. okay, so I will just copy this command. Okay, I will just copy this much. Okay, and I will simply paste it over here with the help of Control Shift V. Right now you just need to press enter. Okay, now it says 58 atoms in the molecule with 62 bonds. So what it has done is that the Perl script has ordered, the bond order is fixed with the help of this Perl script. Okay, and the output file is also lig.mol2. Okay, so it has simply replaced the old lig.mol2 file with a new lig.mol2 file by arranging its bond order. Okay, so this is something that has been done. Okay, so our lig file is appropriately done. Now the next step that we need to do with this lig.mol2 file is that we have to create the topologies for Gromacs. Okay, so we have to create different topologies for the Gromacs, and for that we will go to this Swiss param. Okay, so you have to just copy this address, or you can simply write Swiss param onto your browser. So I will just go to my browser. I will simply paste swissparam.ch. Okay, a window will open like this, or what you can simply do is that you can simply type Swiss param and hit enter. It will just take you to this page. Okay, Now this is basically the server. If you just see it carefully, this server provides topology and parameters for small organic molecules compatible with charm all atoms force field for the use of charm and Gromacs. Okay, so this is something that we wanted to do. So what you do is you it is saying that molecule in mol2 format, all hydrogens and 3D coordinates. So we have to choose the file over here. Which file? We have to select we'll go to home and onto the desktop. If you remember, this is the folder where we are working, which says Gromacs Protein-Ligand main. And here you have to select, or you have to choose the lig.mol2. So I will select lig.mol2 and I will just simply press on select. Okay, so I have selected my molecule and I will press on submit. Okay, now it is saying the results will be available at the following address. You need to wait for at least 5 seconds, 5 to 10 seconds, and then you have to press on this link. The results are not there. Just wait for 5 or 10 more seconds and then you simply refresh this page. And now if you can see, the topology parameters were successfully generated for lig and the results can be found in this zip folder. So now as soon as you click over it, it is not letting me download. Okay, so another thing that I can do is I have to simply I will simply copy this address. I will probably try to open it into another browser. Open Firefox for now. Okay, so I will simply download this lig.zip and it is saying the file has been downloaded. I will just press on this button and it will take me to the downloads folder. So as you can see, this is the lig.zip file that has been downloaded from this Swiss param. So I will simply copy this. Okay, I will go to desktop and I will put it into the folder where we are working. Okay, or I will simply close it, minimize this, and this is the folder where we are working and I will simply paste it. Okay, now what you need to do is you have to open this zip file, and inside zip file, if you just see, there are all the different files that have been created. Okay, so you have to extract this contents into our working folder. So you simply press on extract and press on extract again. Okay, and here it says another file already exists. So here if you carefully see this, I will just cancel. Here the original file is already there. There is a lig file is already there, so it is saying that it should replace it or not. Okay, so what we will do is we will extract, press on extract, press on, I will simply press on extract and I will choose this option says replace nothing. Okay, so I'll close this. I'll also close this. Okay, so all the lig files 1 2 3 4 5 6 7. Okay, so all these lig files are basically the parameter files that are required for the Gromacs to run, whereas this one is the original one. Why? Because we didn't replace it. Okay, so this has to be the original one and the others are the topology files and the other parameter files that are being downloaded from the Swiss param server. So once this is done, you can close the browser. You can close this browser as well, this tab over here as well. I will simply minimize this. Now till now what we have done is that we have done this first, second, 2.3 is done, Swiss param is done. Okay, doc prep is done. Okay, So all these things, from the preparation of ligands and receptors in CHIMERA, all these things are done. Okay, so you should have one folder where you have different MDP files which are already there. You have downloaded it from the GitHub repository. The link is there in the description. And then you separate the protein and the ligand in CHIMERA, save the ligand into the mol2 file, upload the mol2 file onto the Swiss param, and then download the different parameters and the topologies that are required for Gromacs to run. Okay, and paste it inside the working folder. Meanwhile, you also need to have the receptor.pdb file over here. Okay, now we have to now start working with the Gromacs commands. Okay, so we have our terminal over here which belongs to this folder as well. If you want to restart it again, no problem, I will close it. I'll just, in the empty space, right click, open it in a terminal. So the terminal is opened over here, and I will just zoom it a little. Okay, so I've zoomed it a little. Now in order to run Gromacs, what you need to do is that if you simply press GMX, okay, it will say Gromacs is not found. Why? Because in this I have compiled the Gromacs. If you have done the dirty install, then probably the GMX command will run. So for Gromacs to run inside this terminal, you have to just scroll up, and then you have to copy the source file. Just copy this, which will enable this Gromacs to run. I will simply hit enter, and now if I just simply write GMX -- or simply type GMX, it has to show Gromacs over here. Okay, so the Gromacs is now detected. So now all the commands of GMX will run. Okay, so what we will do is that you have to simply now copy and paste the commands which are over here. Okay, so the first command is called as GMX pdb to GMX -f rec.pdb -ingh. So now if you don't have this rec.pdb in this working folder, then probably this command will not run, or definitely this command will not run. So we need to have the rec.pdb. So do not make any mistakes in saving the files from CHIMERA or UCSF CHIMERA. So I will just copy this. I will keep this terminal over here. I will just show it over here. Yes. And I will simply paste the command, and I will hit enter. Now we have to choose the force field which is required. So we will choose the 8 number, which is all charm 27 all atom force field, which is for proteins. Okay, and over here it is also mentioned over here that we have to choose the 8 number and then the 1 number. So I will simply press 8 into the terminal. As you can see over here, I have typed 8. I will do it again, hit enter, and now we have to select the water model. So the best one that is recommended over here, as you can see, is number 1. So you simply press 1 and press enter. Okay, so now it is showing that it has some incomplete ring that is histidine 398. So this is the error that has been shown. So if you find such kind of an error, I will recommend you to do one more thing. What you do is, okay, so what you do is you simply delete the rec.pdb file. Just simply delete it. Okay, minimize this terminal, minimize this codes. Okay, in case if you get this error, if you don't get this error, well and good. You open CHIMERA, go to open, and we will again open the pose1.pdb that we have originally done. We will select the residue or the chain which has the ligand. So we will first select the ligand like this, and then we will go to this actions, atoms and bonds, and delete it. Okay, so we have deleted the ligand. Now you go to tools and then you go to this option which says surface binding analysis, and then you again go to doc prep. Now previously what we had done is that we had unchecked this option over here. Okay, and uncheck this option over here as well. Now previously we had unchecked this time you keep this option on, okay, and then you press OK. It will take little more time, but I recommend you to do this, and you simply press on OK. And what right now it is trying to do is that it is trying to retrieve the different rotamers from Denmark library. So let it do its thing. Okay, so it is done now. Add hydrogens, press OK. Select gas tiger for charges, press OK. The same thing that we had done previously. Go to files, save this PDB and give it a name, capital REC. Suffix should be .pdb, so keep this small tick checked and then press on save. Okay, I will close this. So now you have the newly formed where did I save it? Okay, I saved it over here onto the desktop. I will simply drag and drop it over here. Okay, so I have this rec.pdb which is newly created. I will again open the terminal. I will run the same command. I will press 8, hit enter, press 1, hit enter, and now it is saying that the topologies are successfully created. So whenever you have the commands that have been run successfully, okay, so I will just okay, so Gromacs will give a quote at the end. Okay, so if you get a quote like this at the end, means the command has been successfully executed, and you will also get a notification like this that you have successfully generated the topology from rec.pdb. Okay, so now it has created a new file which says topol.top. Forget about the files that are with 2 hashes over here, so you don't need to care about these files which has 2 hashes in the prefix and the suffix. You can also delete it. Okay, so you have this topol.top file which has been created, which is a topology file for the protein or the receptor. Now let us just go to the tutorial file and see what are the next things that we need to do. So I will just arrange everything properly. I will keep the we'll close this for now. I will just keep the tutorial over here, and then I will keep this file, this folder at the bottom like this. Okay, I will close this folder as well. Where is our working folder? I will just keep the working folder, this one, just keep it open. Okay, so we have converted or the topology from the PDB format into the topol.top. So the topol.top file, as you can see, it is over here, this one. Okay, so that is done. So now let us go and do the next step. So the next step that we need to do is to create a topology and convert the ligand file, that is the lig.pdb file, into the grow.pdb file. Okay, so whenever you see any command of Gromacs, when I'm just simply copying it, okay, and we're pasting it over here. Okay, so wherever you find this -f means the input file and -o is the output file. So that is the basics of this Gromacs. So for this command to run, we need to have lig.pdb. So lig.pdb is over here. From where did we got this file? We got this file from Swiss param, from inside this zip folder. We got this zip folder from Swiss param. Okay, so we will run this file, and let us just see what will happen as soon as we run this command in this folder. So I will just okay, so I will just run this command and hit enter. Okay, so as soon as I executed this command, I again got the quote from Gromacs. It says I have a bad case of a purple diarrhea. Okay, so these are all the jokes or some quotes that you will get at the end. Okay, now the output file that is created is lig.grow. So if you carefully see, there has to be a lig.grow file over here somewhere. Okay, so this one is the lig.grow and this one is the topl-top. Okay, so these two files are created by the Gromacs. Okay, so next thing that we need to do is the topologies of both the protein as well as the ligand separately they are created. Now we have to merge them together. So we have to merge the topology file of ligand as well as the protein. The topology file for the protein is topl-top and the topology file for the ligand is lig.grow. So now we have to merge these two files. Okay, but before we do that, there are a few things that we need to take care of. Okay, so we have to sorry, not topl-top, we have to conf-grow. Where is the conf-grow? Conf-grow is, sorry, I'm very sorry. So conf-grow is the topology file for the protein or the receptor, and the lig.grow. So both the grow files are the topology files for the protein as well as the ligand respectively. So once this much is done, what we need to do is we have to open both the files and we have to merge them manually. Okay, so I will just show you how to do that. The instructions are mentioned over here, but I will just show you how you can do it. So I will just go back. Okay, so you just open gedit. Okay, so this is the command to open both the files into the text editor, and you first type conf, press a tab, conf.grow, and then at the same time, after giving a space, you type a command that is lig.grow. Okay, so lig.grow, the same thing is mentioned over here, conf.grow and lig.grow. So again, lig.g, press tab, and I will simply open it. Okay, so now we have conf.grow, lig.grow, and the tutorial file over here. So we are now interested in the conf.grow. Okay, so conf.grow is basically a file which is containing only the information regarding the protein. Okay, so this is the information which is there only about the protein. Okay, and lig.grow has the information only about the ligand. So what you need to do is that you have to copy it from the third line. So you just copy everything from the third line, select it with the mouse till the end. Okay, so you keep the last line unselected. So you have to select this much from the third line to the second last line. You simply right click, copy it. So you have to copy from the third line up to the second last line, and then you have to go to this other text file which is the conf.grow. So you open this conf.grow, scroll it up to the last, you simply scroll it down at the end. Okay, so this is the end of the file, as you can see. Now at the second last line, you just give an enter like this. So now the second last line has to be the empty space, and in this empty space you simply right click and paste the file. Okay, so now as you can see, what I have done is that I have copied the content from the lig.grow and I have pasted the content at the second last line of the conf.grow file, right? So this is, I have merged the configuration file or the topology file of ligand into the proteins configuration or the proteins topology file. So this is, I have merged two files. Now just click at the last line, and as you can see, the last line is 6931, and over here also you can see it is 6931. Okay, so 6931, you just remember this number 6931, just go up and you type 6931. So there are 6931 numbers of lines in this file, and the first line is not the information regarding the protein, means it does not have the topology information. The second line does not have the topology information, and the last line also does not have the information regarding the topology. So what you do is you have to subtract minus 3. So what will come? 6931 minus 3 should come 6928. Okay, so you replace this number to 6928. So you delete the initial part, okay, by subtracting it by 3, because the first 3 lines, the first 2 lines and the last line does not have information regarding the topology of the protein and the ligand. So you just do minus 3, so you get the number. Okay, so now we have done is we have copied the content of lig into the conf file, and you simply save it. Okay, so if there is any error at this point, then we need to check whether we have created or we have compiled the configuration file. Sorry, I'm saying configuration file, sorry, topology file into a single file. Have we merged it properly or not? We need to check it. Okay, so you just save it, confgrow, close it, liggrow, close it. Okay, minimize everything, and as you can see, where is the confgrow file? So this file is the file we have copied the content from the liggrow and pasted it into the confgrow. Okay, so now let us check whether the copying and making and merging is done properly or not. So for that, there is a very smart way to do this. So simply open UCSF CHIMERA and now try to open this confgrow file. So you just go to files and open, go to desktop and go to this Gromacs Protein-Ligand mains, and you select this confgrow file and press on open. As you see over here, the file has opened properly. Let me just zoom in a little. If there is any error, then your CHIMERA would not have opened this file. And now as the file is open, it means that till now whatever you have done it perfectly well. Okay, so now let us just see where there is a ligand. So I will just go to select residue, and here I have already given the name as lig, so I will select lig actions, and just for now I'll give the color to red. Okay, so we have merged the topology files of protein and the ligand together, and we have created the confgrow file which has the information of the receptor as well as the information of the ligand. Okay, so if this files opens up, then up to now, up to this point, we have done everything perfectly well. Okay, so I will close it. Okay, so we have merged the topology of the protein as well as ligand into the confgrow. So now let us see what is the next thing that we need to do. Okay, so now we have to do some changes into the topol top file. Okay, so it says open the topol top file, so we have to open this topol top file first, and we need to do some modifications into it manually. So you just go to gedit, give space topol and hit enter. So here there is the topol top file. So let us see what changes we need to make over here. So now let me just go to this Gromacs codes tutorial, and it says once you open this topol top file, we have to add something. So what we need to add, we have to add this much, the 2 lines. Okay, so I will just copy this. Below, include force field parameters. So you have to search for this inside the topol top file. So as you can see, this is the same thing that we have mentioned in the tutorial. Go to Gromacs codes and we have to add it. So you have to add this part below this. So I will just hit enter and simply paste it over here. So we have added these 2 lines. Okay, so we it says include ligand topology, include lig.itp. So this 2 lines we have to add it into the topol top file. Now what is the thing that we need to do? Now it says at the bottom of the same file we have to do some changes. So now what we will do, we will just go to the bottom of this file, and here at the last line you give enter, and you write lig, give space and write 1. Okay, so this is something that they have, or it is mentioned in the tutorial. Okay, so we have to add lig1, align it exactly below protein chain 1. Okay, so that is what we have done. Protein chain A1, exactly below it we have aligned the lig1. So as you can see over here as well, exactly onto the last line we have added lig1. So this is something that we have added, and we have added the include ligand topology on the top. So we have made 2 corrections in the topol top. On the top we have added this much, 2 lines, and at the bottom we have added lig1. Okay, so and once you have done this much, you press on the save button and close the topol top file. Okay, so we have added the topology parameters and everything is done. Now it says edit the following in lig.itp. So in most of the cases, this is very important, in certain cases this will already be lig3 for most of the cases, so there is no need to change it. So if you are using the CHIMERA and if you have used or prepared the protein and ligand with the help of CHIMERA, then probably this correction you don't need to do. I will just show you, still I will show you what we need to do. So lig.itp, where is the lig.itp? This is the lig.itp, it is in the capital. So just let me open gedit space lig.itp and press enter. So what it says is that as you just scroll down, there has to be something which says lig.3. It is already there, so we don't need to change it. So let me just go to the Gromacs codes, the tutorial, and it says it has to look something like this: molecule type, semicolon, name, NREXL, lig3. So just let us see the same thing is there or not. Molecule type, name, NRXL, and lig3. So it is already there, so we don't need to do any changes, but you just check it once. If you need to do this, you have to do this. If it is already there in this format, then no need to change it, so you simply close it. Okay, now most of the things are done till now. The next thing that we will do is that we have to create the virtual box around the protein and the ligand complex. So for that, what you do is you simply need to copy. Now most difficult part of this Gromacs is done. Now simply you just need to copy and paste these commands over here. So you just copied the command and simply paste it, hit enter. Okay, it says Gromacs reminds you, oh my god, it is funky shit. Okay, so this is the code that we got. So the command has been done properly, and the output file over here is -os box grow. So as you can see, box.grow, where is the box.grow? So this file has been created. Now it says gmx solvate. So now in this solvate command we will use, and we will fill the box with the solvent. Okay, so we will fill this box, the virtual box, with this water molecule. So you simply copy this and you simply paste it and hit enter. Okay, so Gromacs reminds you, you are insignificant. Okay, so this is something that is done. Okay, so the output file is box.sol.grow. So if you just want to visualize how this box looks like, what you can do is you can write VMD, virtual molecular dynamics. This software we have installed it in our previous video, or in the last video I showed you how to install VMD. So you just type VMD and you simply give this name, which is box_sol.grow. So you just let us see, we have to open this file in VMD. So it is box_sol. I will give a tab button, it will automatically take, and I will hit enter. So as you can see, this is the virtual box that we have created, and in center you can see the protein and the ligand complex, and around it in this virtual box we have filled this box with the water molecules. Okay, so we are preparing the system right now. So this is how your system looks like at this point. So we are getting the things ready for simulation. So I will just close this for now. Yes, we really want to quit. Press yes. So now let us move ahead with the next step, which says that we have to make use of the gromp command. So here you need to have the file which is ions.mdp because it is -f. ions.mdp is the file which we have already kept it inside this folder, which is this one. From where did we got this file? We got this file from my Github, which is ions.mdp file. Okay, so I will just close this. Okay, so you need to have this ions.mdp file into this working folder, otherwise this command will not run. So you just copy this command, and output file you will get it as ion.tpr. So I will just paste it over here, and you just keep an eye on this folder. You will create a file which is ions.tpr, and I will hit enter. Okay, so where is ions.tpr? ions.tpr. So this is the file that has been created by this command. So if in case if there is an error, or if it asks to make use of max1, then you may need to use this command, but on the priority note you just use the first command. Okay, so this command has been executed properly, so you just eliminate this command. You don't need to do this. Both the commands means the same. Now what do we need to do is we need to make use of the genion command. So genion, so you just copy this command and simply paste it, and here it is telling to choose the group number 15. So group number 15 is what? It is the sol. So you just type 15 and hit enter. If the sol is somewhere else, so if suppose if you are doing something else and if you get this option at number 13 for instance, okay, then you type 13, but make sure that corresponding to the 13 there has to be a sol over here. In this case the sol is appearing at number 15, so we will press 15 and hit enter. Okay, so it says Gromacs reminds you here the way it might end, means your command is appropriately executed and it has added all the CLs. Okay, now the next thing that we need to do is you can call it as energy minimization.mdp file. Okay, so we are going to use a command which is a gromp command. So I will just copy this. For this you need to have an mdp file. From where do you get this mdp file? Again, we have downloaded this mdp file from my GitHub. So it is this file that they are talking about. So let us just copy this. Copy and simply paste it over here. Okay, so it says Gromacs reminds you microbiology lab steps only. Okay, so staphylococcus they are talking about, steps only. Yeah, so as you can see the command is successfully executed, and as you can see output is em.tpr. so em.tpr file has been created somewhere around this folder. Where is em.tpr? That is this one. Okay, so em.tpr has been created. Now this is the first md run command, which is the energy minimization. So em stands for energy minimization. So the first md run that we will do is for the energy minimization. I will just paste the command. It can take up to a minute or 2 or 3. So I will just hit enter, and it is doing its own calculation. So whatever is happening right now in front of you is the energy minimization steps that have been going on. Okay, so now it says that the energy minimization has been done. Okay, and the values regarding the energy minimization is represented over here, and you again get a quote at the end, means your command is successfully executed. Now what we need to do is that we have to I will just it says that gedit we have to modify the nvt files, but we have already modified it. I have already modified and kept it over here, so you don't need to worry more. So now it says that we have to make the index files. Okay, so you just copy this command. So we'll use the lig-grow file as the input, and the output file you will select the index_lig.ndx. So I'll just copy it and I will just paste it over here, hit enter. Now it says 0 and exclamation AH. So if you simply copy this, it's well and good. What each thing means, it is shown over here. 0 means system. And what does end mean? End means only end. Exclamation, everything is mentioned over here. Just read it once while you are doing it. Not only system, not A and H. Okay, A is atom and H, capital H is there, so that is something that you have to simply paste it over here, star, and hit enter. Okay, and once this is done, press Q and hit enter. Okay, so after this there will be a file that is created which is called as index_lig.ndx in this working folder. So just let us see that whether that file has been created or not. So we'll search for sorry, it is index, right? So index, here it is. Okay, so index.lig.ndx is created by this command. Okay, now we need to make use of the genster command. So I will just use this and just copy this and simply paste it. So these are the universal commands that I have created for you. So select group number 3. It does not matter whether you are using the same protein or the same ligand, as far as you are saving the protein and the ligand as rec.pdb and lig.pdb at the initial stage. Sorry, lig.mol-mol2. All these commands will work absolutely fine for you. Okay, now it is saying that we need to do some changes in the topol-top file. So now let us just do that. Okay, so it says open the topol-top file again. So we are now going to open topol-top. So it is gedit topol-top and hit enter. So the topol-top file has opened in front of us. Let us just see what are the things that we need to do in this. So after include position distance file ifdf, so you just search for this somewhere in this topol-top, include position distance file. So where is it? Okay, so it says include position distance file. So this is what they are talking about at the bottom of the page. So scroll down, you will find this include position distance file. So after this you have to add, just copy it, just copy this much, and at this point you just add this much. Make sure everything is properly aligned. Okay, so you have added this much. Now let us see what else do we need to do, and you have to save it, and then you have to again make the index file for the system. Okay, so you just go to topol-top and save it. So topol-top is saved. I will just close this topol-top for now, and now we have to make another index file. So that is gmx make ndx em.grow. Output is again index.ndx. So just copy this, paste it, and now it is telling to include 1 and 13. So let us just see what is 1 and 13. So 1 is protein and 13 has to be ligand. So yes, 13 is ligand. Okay, so what you do is copy this. It has to be protein and ligand corresponding to it. Oops. 1 and 13. Press enter. So it is saying that it has created protein and lig complex index file. Press Q and hit enter. Yes, so it is saying the code has again appeared in front of us, means that the command is properly executed. So this is done now. So we have done most of the parts regarding the system building and the minimization, etc, etc. The most crucial thing that we are now ending up over here is that we have to do the initial run with the help of NVT. Okay, that is called as equilibration run. So for equilibration run, what we have to do is that we need to have this NVT file. Okay, so we have to search for NVT file. So where is NVT? Search for nvt.mdp. So just open this file once. So now when you open this file, it says that equilibration will be done for 100 picoseconds. So that is okay, you don't need to change anything over here. Why I'm seeing an error over here, just let me check it once. Let me open npt file. Where is npt? Where is the npt file? Okay, here it is. Npt is also the same. Okay, so it says number of steps that you have to do. Okay, and it is for 100 picoseconds. So I will just copy this 100 picoseconds. So just copy this. I will do this correction in my GitHub, so you don't need to do this. I will just npt. So I'll just close this. NVT, I have open NVT. Make sure that this is appropriate, otherwise you will end up in error. So yeah, so we will do the equilibration. First step is NVT equilibration. The next step after this would be NPT equilibration. So let us first do this NVT equilibration for 100 picoseconds. We'll just save it. Make sure everything is as it is. Make sure that the number of steps is as good as this. So now suppose if you want to change these numbers, I will just show you how you can do it. If I add 1 0 over here, you have to add 1 0 over here, and you have to add 1 0 over here like this. Okay, so if it is say 5 lakh steps is equivalent to 1000 picoseconds, that is 1 nanosecond. But now we are doing only for 100 picoseconds, so you have to remove 1 0 from here, 1 0 from here, and 1 0 from here. So this is how you can change the numbers and change the time of MD simulation that is to be done. I'm just saving it for now. Close this nvt.mdp file, and I will simply run the command which is mentioned over here. Okay, so I will just copy this command. I will just paste it. Okay, wherever you find this max1 -2, okay, so first try to run the command without max1, and if you run the command with max1 as well, it is okay, but we will just try it without max1 for once. Okay, so we got the quote, means the command is executed properly, and now we will make the command for MD run, for MD simulation run. Okay, so that is the command which says gmx MD run. So this will do the first 100 picosecond MD simulation for equilibration. So if this becomes a success, then congratulations, you have reached to the point where nothing can go wrong. If this command is executed properly, then everything is good to go, and I will give enter. Depending on the computer speed, it will take time. So So congratulations, your first MD simulation for equilibration has been started. So we will wait till this gets done. Now, depending on the computer speed, depending on your GPU or CPU, whatever your computer is trying to do, it will take time. So we will wait for this commands to be done. Okay, so the MD run for NVT is complete, and as you can see on to your screen in the terminal, it says your shopping techniques are amazing. So again, we got a quote, means your command is successfully executed, and there are some information which has been mentioned over here, and it is telling me the performance. It is showing me that for this protein, my computer with the graphic cards is giving me the speed of 43 nanoseconds per day. Okay, so if your protein is small, then you will require, or the speed will be higher. This is relatively a huge protein, so I'm getting the speed of 43 nanoseconds per day. If your protein is say 30 or 40% smaller than this, then you will get the speeds with this kind of GPU, which is the NVIDIA RTX 2050. You will get the speeds up to 100 nanoseconds per day easily. So okay, so let us just continue with this tutorial. The next thing that we need to do is that we have to do the same thing with NPT. So the NVT equilibration is done. Now we have to do the NPT equilibration. Okay, so NPT equilibration that we are trying to do over here. So we have already seen the NPT file. It is again 100 picoseconds. So we will just copy this command, and in this case you keep max1. It's okay if you remove this max1 option, like max1 2, you can keep it, you can remove it. So I'm just keeping it for now. In the previous I had not, so let me just and hit enter. Okay, so the command is successfully executed, and now we will do the MD simulation for NPT. Just copy this and paste it over here. I will give enter, and the simulation run for the equilibration by making use of NPT is done, or it is executing right now. So we will wait for a few minutes till it's done, and as you can see onto the screen, it says as one GPU selected for this run. So this is a very good indication that your system is successfully using GPU for this simulation run. Okay, so again the command is successfully executed, and you got a quote at the end. So now let us just go to the last part of MD simulation run. So for that, what you need to do is that you need to have this md.mdp file with you. And here there is a mistake that I will change it. It has to be md.mdp file. So you just open the md.mdp file, and here you need to choose how much long duration you want to keep for MD simulation. So I will just show you that how to do it. So it says md.mdp file. So you first of all search for md.mdp. md.mdp. I'm not able to find it. Okay. Okay, so this is the file which is md.mdp. So I will just open this mdp file. Again, from where did you get this file? From the GitHub file repository. And now it says that it is for 10 nanoseconds. Okay, so now let us, for this tutorial, what I want to do is that I just want to do the MD simulation for 2 nanoseconds. And now if you want to publish your data somewhere, and if you are doing some sort of a research, then I recommend that at least you need to run your MD simulation for 25 nanoseconds at least. If your protein is of a reasonably small size, if your protein is large in size, then probably you need to go up to 50 nanoseconds or 100 nanoseconds. But for this tutorial video, what I will do is that I will just run this for 2 nanoseconds, and let us just see what are the changes that I need to do for this. Okay, so as you can see, if I just remove 1 0 from here, it will be 1 nanosecond. I have to do 1 0 from here as well, and 1 0 from here. Okay, and now if I want to do it for 2 nanoseconds, then what should I do? I want over here it has to be 2. Okay, so what I will do is that I will do 2 over here, and for that I will replace 5 with 10. You just count it and you replace 5 with 10. Okay, so this is 2 nanoseconds. Okay, so n steps. Let us just close without saving this. I don't want to save it, so that I will repeat it again so that you understand. Close without saving. Minimize this. I will again open this md.mdp file. So if I just remove 1 0 from everywhere, it means the calculations are for 1 nanosecond. But now if you want to do 2 nanoseconds, then what you do is you replace 5 with 10. So you double the first, you double this number of steps. Okay, so you double the number of steps over here. So you just replace this 5 with 10. You replace this 5 with 10. So this will become 2000 picoseconds, and here it will become 2. And then you save this file. Okay, all the other things that you may need to do, I have already modified it over here as well. I have also changed the title for MD simulation. Okay, so this is basically the main MD simulation file that you should be concerned with. If you want to do it for 20 nanoseconds, you just add 1 0 at the back. Similarly, you just calculate how much you need to do for 25 nanoseconds, how many steps you should include for 25 nanoseconds. So it is up to you. You have to change it as per your wish. For now, I am just keeping this for 2 nanoseconds because this is just the tutorial video that I want to show. So I'm just saving it for now. And once you save it, close the file. And then what you do is you have to just copy this command. It will make use of the output of the previous NPT equilibration as the input, and it will then run the MD simulation. So I'm just copying it and I'm pasting it. So once again, we have done 2 equilibration MD simulation, that was NVT and NPT, and now we are doing the final MD production run. So this is basically called as the production run of MD simulation. Here you can choose how long you want to keep your the MD simulation run, whether it should be for 2 nanoseconds, 5 nanoseconds, 25 nanoseconds, 50 nanoseconds, 100 nanoseconds. Here you have to change the parameters inside the md.mdp file as I've just shown you. And once you do this, yes, it says that the Grom command is successfully executed. You got the quote at the end. And now the last thing, the last command that you need to run. Okay, and as soon as you start this was the last command that we are discussing in this video. After this, whatever we will do will be considered as the post simulation assessment, like creating the videos, creating the graphs of MD simulation, etc., will be the part of post simulation. So if you reach to this point and if you are successfully running all these commands, means that you have successfully performed the MD simulation production run. Okay, so we will wait for this simulation to be done. As it is 2000 picoseconds, which is 2 nanoseconds, it will take some time. With this kind of a computer speed that I'm getting, it will take around 2 hours. So the final MD run, which was also called as, or which is also called as the MD production run, is also successfully completed. As you can see that the Gromacs is again given a quote at the end. Now if you see carefully, it has shown us that what is the performance of this system. For this protein, again for this production run, the speed that we obtained on this system was 42 nanoseconds per day. Now I will show you what are the output files of this MD run, and at this point your MD simulation is considered to be complete successfully. And once you are done with this MD simulation with the production run, you should know which are the output files that you get. Okay, so I will just show you the output files. Now before you understand what the input files were and the output file should be, you just need to see the commands that we gave. Okay, so these are the last two commands that we provided. So md.mdp file was the input one, so this is basically the input file, and the output file that you got was md.tpr. Okay, and then once this command was successfully incorporated, we did the MD run, and after that we got different files in our working directory. So if you just see over here, these files, which are md.cpt, edr.grow.log, .tpr and .xtc, these are basically very important files, especially md.tpr and md.xtc. These are very important files. Why? Because they are the output files of final MD production run, and these files are also called as the trajectory files of MD simulation. And ultimately after the MD simulation, you will be using these final files to assess the trajectories, which is the output of MD simulation run. Again, you can use these files to construct the video of MD simulation run. So for this video, I think this is the sufficient information that I have provided you. I have shown from A to Z the entire procedure of performing molecular simulation dynamics for any protein ligand in Gromacs with the universal commands that I will be giving it to you, and you can also find it onto my GitHub page. And in the next video, I will show you how we can visualize the output trajectories of MD simulation run, and we can create, and how we can create the videos or a video of this MD simulation outputs that we have got. And in this thank you for bearing me for the entire video. I will catch you soon into the next video, where I will be showing you how to visualize this output files for MD video. Okay, so thank you. Catch you in the next one.